Okay, everyone. So I just I posted this science packet to the Google Drive, which Mr. Prednia has set up. There's a folder in there for 7th grade science, but for your convenience right now, I have the review up on the screen. So everyone get started. Let's put pencil to paper. I know that you may need to use a piece of loose leaf or scrap paper to do this. Please do that. Let's take about 3 minutes on the review. Remember that if it's false, explain why it's false. So like correct it or explain why it's false. So we'll take 1 more minute. On the review, and then I'm going to actually take volunteers. We'll go down the list A through F. Actually, may even just call on people. I'll take volunteers first, but I will not waste time, and I will just call on people to share. So about another 30 seconds. Okay, so let's go through these true and false answers. If it is false, explain why. A, waves are created by a vibration. Actually, let's do it like this. We'll do true and false, and if it's false, then I'll pick on someone to explain why it's false. Okay, so true, just put up an agree for true. Okay, agree is true, and disagree is false. So waves are created by a vibration. Is that true or false? Or do we agree with this? The answer is true. Yes, they are created by a vibration. B, as a wave moves through a medium, the individual particles of the medium move from the source of the wave to another location some distance away. Is that true or false? Do you agree with that or disagree with that? I thank you, Jessica, for following instructions. There are there are actually many people who are not showing whether or not they agree or disagree. Jessica, tell us why this is false.
I think this is false because in the part B, it says the individual particles of the medium move from the source of the wave to another location some distance away. But I disagree. with the part that says some distance away.
Okay, so what do the particles do? Instead of going from one place to another, what do they do? Jessica.
Um,
Tanzel had his hand up.
All right, Jessica, we'll give Jessica a little bit of shine. Think about it for a second.
I think they like, I don't know.
Okay, Tanzel, let's help our classmate out here. What do you think, Tanzel?
The particles vibrate in a fixed position.
Yes, the particles, so they don't move from one place to another. They move back and forth, but there's no net movement. If they move up, then they move back down. Or if they move left, then they move back right. But they never go from point A to point B. That's actually the energy that moves from point A to point B. So let's go to C. Are waves a means of transporting matter from one location to another? Agree or disagree with this? Agree or disagree with this? Thank you, Chanel, for showing whether or not you think you agree or disagree. Carlo, Morris, let's see, who else? Okay, Carlo, why do you disagree?
With a 2 meter up.
I disagree. I'm confused.
Okay, what do waves transport? Remember, there were two really, really important things that we had to remember from class yesterday.
We had class yesterday.
Carlo, who's speaking on your video?
I don't know.
Carla, is there TV on in the background? Just turn it off.
All right. Waves transport energy. They do not transport matter. This is false. Waves are not a means of transporting matter from one location to another. The matter doesn't move from one place to another. It just goes back and forth.
Mr. Amador, I have a question.
Yes.
So in order for teleportation to be true, would you think that waves would now need to start moving matter?
I can't really like get into that because that's like gonna bring us down a deep rabbit hole. There's actually, if you want to look into like quantum, if anyone wants to look into some things, quantum mechanics, there are actually videos online which are very accessible. On the very, very smallest scales, you can actually think of kind of teleportation actually really does happen. Because matter does go from one position to another without traveling in the space between it. It disappears from this location and appears in that location. But we don't observe that on large scales. We only observe that on the very tiniest of scales. All right. D, an ocean wave will not transport ocean water from near the middle of the ocean to a location near. This is true. It will not, because the water is the actual medium. It is matter, and waves do not transmit matter. They transmit energy. E, as mechanical waves move through a medium, particles of the medium undergo a periodic and repeated vibration about a fixed position. This last part, about a fixed position, means you can imagine that if it starts here, it moves and then comes back to its original position. Do we agree with this? Is this how mechanical waves work? The medium moves and then comes back to its original position? Yes, this is true. This is how mechanical waves work. And finally, the particles of a medium have the ability to do work. Do the particles in the medium have the ability to do work? Bailey, why do you say no?
Wait, hold on. I don't know because don't they just like move, then move back? But it's not, they're being pushed by something. So like if I had pushed this water bottle, I don't know if it has worked because I'm doing the work on it because I'm the thing that's making it move. So like I don't think.
Okay, so here, think about this. You used a water bottle example. So here I've got two glasses that were on my desk. If I'm doing work on the first mug, but then when the mug hits the glass, the mug is pushing the glass. So this mug then does work on this glass, and we're going to learn about that today. The answer to this is yes. The particles do have the ability to do work because it's like a chain reaction. One particle bumps into another particle, which moves that particle, and then that particle hits another particle. So it's a chain reaction where they do work on each other, and that's what allows the wave to move through the medium. So going on here to the PowerPoint, switching over to the PowerPoint slide. Give me a thumbs up if you see the PowerPoint now. Okay. So the main important things, the main notes, which I, go back slideshow. The main points which I jotted down, these are the most important things we need to remember from yesterday, is that waves transmit energy, but not matter. The medium is the material that the wave energy travels through. So if you think about sound, the air is the medium that sound travels through. If you think about ocean waves, the water is the medium that that wave is traveling through. But that material moves back and forth, it vibrates, but it does not get transmitted from one location to the other. It comes back to its position. And we're gonna watch a cool video of that happening with Slinkies today. So today's goals are to learn about how mechanical and electromagnetic waves, oh, I guess I can't erase right now. Okay, learn how mechanical and electromagnetic waves work. And there are two different types of waves, which are longitudinal and transverse waves. The first thing that we're going to learn about today is the difference between parallel and perpendicular. What does parallel mean? Jason, parallel, go.
Parallel means like in the same, it's like two lines that that can keep going on and on, but they never touch.
Excellent. Yes, two lines that go on and on forever. They stay the same distance, but they'll never meet. So if we say in a direction parallel to, you can think about, take a look at this image here. So imagine like a little car, which is moving in this direction. The direction which is parallel to the car is the purple line, and the red line is the direction the car is moving. So those two lines are parallel to each other. Let's review perpendicular. What does perpendicular mean? What does perpendicular mean? Jalen, are you with us?
Yeah.
What is perpendicular?
Perpendicular means
If you look at the screen, there are two examples of perpendicular lines.
I don't know how to describe it.
Okay, so give it a shot, and then we'll give it a start, and then if you need help, we'll finish it.
It's like opposite from, what's the opposite Well,
What do you notice? What do you notice about these two examples here of perpendicular lines?
they're straight up from the other line.
Okay, what angle do they have between them?
90.
90. So specifically 90 degrees. Perpendicular lines are lines that are at right 90-degree angles to each other. So when we talk later today about waves that vibrate perpendicular, you can imagine here that, let's say the car is moving in the direction that the wave is moving, right? The energy is moving in a direction. So that's the car. The perpendicular direction would be that red line, 90 degrees away from it. All right, so transverse waves. We're gonna read about transverse waves. So I gotta switch again. Let's switch over again to the packet and read about transverse waves. So remember that our goal over here is to learn about the two types of mechanical waves, transverse waves and longitudinal waves. I'm gonna read actually the first one on transverse waves, and we can do some popcorn reading later. So I'm gonna zoom in here on transverse waves. Okay. Transverse waves. When you make a wave on a rope, the wave moves from one end of the rope to the other. But the rope itself moves up and down, or from side to side, at right angles to the direction in which the wave travels. Waves that move the medium at right angles to the direction in which the wave travels are called transverse waves. This is important here. That's key. This is our vocab word. Transverse means across. As a transverse wave moves, the particles of the medium move across or at a right angle to the direction of the wave. The high part of a transverse wave is called a crest. This is also important. And the low part is called the trough. Trough sounds like this, T-R-O-F-F. That's how it sounds, but it's spelled with an O-U-G-H, trough. So I'm going to keep this up on the screen. I want everyone to write, based on what we've just read here, how can you make a slinky move to produce a transverse wave that moves from left to right? Take 1 minute to write down your ideas, and then I'll show you a video of it. I'm going to call on Kaylin after the minute, so you got about 45 seconds left, and then Kaylin, share out your idea. This is a bit of a picture down here I'm also showing you. So you basically want to make the slinky move like that. You want the direction of the wave to go from left to right, but you want the slinky itself, the medium, to move up and down. Perpendicular. Perpendicular to wave direction. All right, Caitlin, go ahead and mute yourself. How would you accomplish this in real life?
I'm not really sure because I wasn't able to read the text because I just got back on.
Okay, so I'm gonna leave the text up. Go ahead and read it now, and I'm gonna call on someone else. So read through it yourself now. Let's go to Leilani. How do you think that you would? Hmm?
The question at the
Yeah.
bottom.
How would you move the slinky to produce a transverse wave that moves from left to right?
It's like when you move, because it says in the text that when you make a wave on loop, it moves from one end of the loop. So you know you should, you know, with this thinking, you wiggle it.
Wiggle it, yeah, wiggle it. Okay, so be more specific because there's so many ways you can wiggle something. Are you gonna move your hand in a circle? Are you gonna move it up and down? Are you gonna move it left and right? Diagonal, all crazy directions? What are you gonna do?
Left and right.
You're gonna move it left and right?
Yeah.
Okay, so that's an idea there. Let's take a look at how we would produce transverse waves. I'm just gonna go ahead and share computers. Okay. Give me a thumbs up if you see the video.
I just want to show you a demonstration of transverse and longitudinal waves using a slinky. Now, transverse waves, the direction of energy is going to be going forwards, and that's the same with longitudinal waves as well. The energy is going to go this way. But with a transverse wave, the medium, so in our case the slinky, which is what the wave is going to travel through, is going to be moving perpendicular to the direction of energy transfer. So let me give this a go.
Can you all still hear me? Give me a thumbs up if you could hear my audio. Okay, so the way that he's moving his hand is he's shaking the slinky up and down. Okay, so he's shaking the slinky up and down, but the wave is traveling from left to right.
So you can see the pulses or the waves are moving from the left to the right. So the energy is moving from the left to the right, but the actual slinky itself is moving perpendicular to the direction. Now, another kind of wave is a...
Okay, so the next one he's going to show is a longitudinal wave. So let's go ahead into our packets and let's get a volunteer to read. So the definition we have here of transverse waves before we move on. Jessica, I see your hand is up. You want to read, Jessica? Let's write this definition down first. The definition is a wave in which the medium vibrates perpendicular to the direction of wave. I'm running out of space here. I don't want you to get confused. Of wave motion. Okay, you can rephrase that in whatever way makes sense to you. But basically the idea is that if the medium is moving perpendicular to the direction that the wave is traveling, then it's a transverse wave. All right. We also have to label here the crest and the trough. So let's go back to these vocabulary words real quick here. The crest is the highest point in the wave, and the trough is the lowest point in the wave. So I'm going to just label these crest because A is the highest point there. B and C are neither the highest nor the lowest. D is the lowest, so this is called a trough. E is not highest or lowest. F is another crest. And I is another trough. if you wanted to just write these notes on your own paper, you could just do something simple like this, and you could just label crest and trough. Super simple. Just mark those points right there. Crest and trough. Okay. First paragraph of longitudinal waves. Jessica had her hand up.
Okay. A longitudinal wave is a wave in which particles of the medium move in a direction parallel to the direction that the wave moves. The coils in the spring move back and forth parallel to the wave motion. Suppose that a slinky is stretched out in the horizontal direction across a classroom, and that a pulse is introduced to the slinky on the left, ending by vibrating the first coil left and right. Energy will begin to transport through the slinky from left to right. As the energy is transported from left to right, the individual coils of the medium will be displaced leftwards and rightwards. Longitudinal waves are always characterized by particle motion being parallel to wave motion.
Thank you. Next paragraph. Let's go to Bailey.
Okay, so you want me to read, right?
Yeah.
And starting from the parts, okay. In some parts of the slinky, the coils are close together. In other parts of the slinky, the coils are more spread out. The parts where coils are close together are called compresses. The coils spread out or
rarefied. Mhm.
Rarefied. Thank you. Are called refractions, I think. Fractions?
Rare
Yeah.
refractions.
Rarefactions.
Rarefactions, yes. Yep, very good.
Okay. As compressions and rarefactions travel along the string toy, each coil moves out. Each coil moves forward and back. The energy travels from one end to the spring to the other, creating a wave. After the wave passes, each coil returns to the position where it started.
Thank you, Bailey. Morris, what does it mean to be compressed? In a longitudinal wave, what is a compression?
Compression, I think, is like when it's closely packed together, it's like the slinky is like for example, if I had a slinky and there was like no gap, barely any gaps between them, like that would be compressed.
Okay, close together, compressed. Daniel, are you able to hear me? Okay, let's go to Tanzel. Tanzel, what is a rarefaction? Tanzel, can you hear me? Thank you.
Yeah. Rarefaction is when the like the coils in a wave, like where the parts of a wave are like spread out, I think.
Absolutely. So remember that earlier we learned about the crest and the trough in a transverse wave? The crest is the high point, the trough is the low point. This is similar but different for longitudinal waves. The compression is where the wave, all the particles are closest together, and the rarefaction is where they are more dispersed further apart. Let's take a look at the video of this. So let's go back to our video. If you're, just check if you're unmuted and mute yourself, please. All right.
Go quickly, Daniel.
So let's see a longitudinal
wave. Now with a longitudinal wave, the medium, again, which is the slinky, moves in the same direction as the energy transfer. So the energy is moving in this direction. Our wave is going to be, or the medium, the slinky, is also going to be moving in this direction. So this is a longitudinal wave, like sound is also a longitudinal wave. So in this case, you can see that there's a part where the wave gets compressed and a part where the wave gets rarefied, and that these pulses move along in the same direction that the energy is flowing. So that's a longitudinal wave, like that. That's a transverse wave. Okay.
Okay. So for longitudinal waves, what I want you to do is I want you to take a look at this portion here. Read about this longitudinal waves. It talks about how sound waves work. It describes that energy transfer from particle to particle. And then using the information that you're reading, see if you can draw what the longitudinal wave looks like. And you're going to draw that. If you actually have the packet, you'll draw it right there. And if you don't, just draw it on a piece of paper. Don't be fancy with it.
Mr. Alder, do you know where Caitlin is?
Can you repeat?
Do you know where Caitlin is?
I'm not sure. Let me check the chat and see.
No, yeah, me and Miss Tinky were just discussing, so we're just gonna see if she comes back.
Okay, thank you. I know Tanzel went to use the restroom. I'm not sure if he's returned yet. Okay, he's back. So we're going to take 2 more minutes to finish reading this and then drawing what a longitudinal sound wave looks like.
Bailey, sit properly, please.
And in that time also write the steps, outline the steps of, so basically if you follow the directions to completion, it says write the steps that lead to a sound wave reaching the ear. So underneath, just jot down a few of the steps. You don't have to have exactly 4 of them as long as you express the idea clearly. I'm going to start to annotate a few things in there. So if you're still thinking, I'm going to draw a few supports in here to help you along. We know that the wave transmits energy from the lips of the speaker to the ear of the listener. So we know that the energy is moving from left to right. Let's go to Carlo. Carlo, what's an important feature? So I'm going to draw in here what the particles in the air would look like. What is an important feature of longitudinal waves? How can we tell from looking at something that they're longitudinal?
we can tell that it is longitudinal, how you say it?
Longitudinal.
But
You got muted there. Carlo, can you unmute yourself? It's not working for me. Okay, Morris.
working
Carlo.
now?
There you go. Go ahead, Carlo.
Okay, so the way we find out if it is a longitudinal,
Okay, you got muted again, Carlo. So I'm unfortunately I'm gonna have to skip over your turn. And so if we have particles in the atmosphere, the key characteristics that we could visually see are those compressions and those rarefactions. So I'm gonna go ahead and I'm gonna draw in the compressions where the air particles would be close together. And the rarefactions are the areas where the particles are further apart. So this would be a compression. I'm just going to put a C. This would be a compression. This would be a compression. And basically all the spaces in between you could consider to be the rarefactions. Jason.
Yes.
What are the steps? What are the steps for how sound waves reach the ear of the listener?
The steps of how we reach the ear of a listener is so we do that. What we do.
I'll start you off so you know what I mean by that. So for example, when the speaker speaks, their vocal cords vibrate back and forth, and they hit the particles in the air. So it compresses the particles in the air, and one particle then bumps into another particle. What do you think? Continue on from there. What happens after that? That was in this, basically we're summarizing this reading that you did, which I put back on the screen.
Yeah. So I think
everyone else, if you haven't finished this part yet, you're also thinking about it, writing it down as well.
so. It says how each of those individual particles pushes on the neighboring particle, the neighboring particle, and it pushes it forward.
Mm-hmm. And it pushes it forward. So it's kind of like a chain reaction, where are you guys able to see my fingers? I've got 4 fingers up in the air. Yeah. So they're spread out now. If I pushed my pinky in towards my other finger, I'm causing a compression. My pinky will push these 2 fingers together. And now there's a rarefaction between my pinky and my ring finger. I bump into my middle finger, which is then going to push over to my index finger. And this is very hard. I'm not dexterous enough to do that. That would be pretty cool if I could do that. All right. So for homework, what I want you to do is to finish this independent practice, which is labeling the diagram using, so there's 3 questions here. So do questions 1, question 2, and question 3. To wrap up the key points of today's lesson, there are 2 types of mechanical waves. Jessica, are you raising your hand to summarize the key points?